Welcome to the Deep Dive. Today, we're talking about software testing. Now, a lot of people, I think, see testing as maybe just the final hurdle before software goes live.
Right, like the last checkpoint.
Exactly. But what if that whole idea kind of misses the bigger picture? What if testing is actually, woven through the entire process, guiding things, speeding them up?
Well, that's pretty much what we're going to unpack. We've got this really detailed document that looks at how testing sits into the whole software development lifecycle.
Okay.
And it shows how different ways of building software, they really change how you test. And it gets into some key concepts, explaining why testing looks the way it does in different situations.
So our mission here isn't just to list what tests happen, but to dig into the why. Why then? Why that way? Hopefully by the end, you'll have a clearer, more sort of connected view of how testing all fits together.
Sounds good. Let's challenge that final step idea.
All right. So our source material kicks off right at the foundation. How the way you decide to build software shapes everything else, testing included. It introduces this concept of a software development lifecycle model, or SDLC.
Yeah, an SDLC model. Think of it like the overall plan or recipe for building your software. It's kind of an abstract way to map out the process, the phases, the activities, the order things generally happen in.
And the document gives examples, right? Different kinds of plans, like the sequential ones finish phase A, then start phase B, waterfall, V model, those sorts of things.
Mm-hmm. And then you've got iterative models where you kind of cycle back and refine things, like the spiral model or prototyping, and incremental ones where you build it piece by piece, like the unified process.
And we can't forget the more, let's say, flexible approaches, agile methods like Scrum, Kanban, XP.
Definitely. And the really crucial thing to get is that picking one of these models, it's not just some technical detail. It basically dictates your entire testing strategy. It has a huge impact on when testing happens and what kind of testing happens. The scope, the timing.
So it goes beyond just timing. It affects things like how much test documentation you need.
Absolutely.
Yeah.
Documentation, the specific test techniques you choose, your overall approach, how much you rely on, say, test automation,
right.
Even who does what. The roles and responsibilities of the testers themselves can change quite a bit depending on the model.
Okay, let's contrast that. So take a sequential model, like waterfall. You mentioned testing happens later.
Typically, yeah. Especially dynamic testing where you're actually running the code. In waterfall, you spend a long time on requirements, then design, then coding. Only then do you really have something substantial to test dynamically. Testers might review documents earlier, sure, but the hands-on testing, that's pushed towards the end.
Right. Now, compare that to iterative or incremental ways, especially agile. The whole point there is getting working software out much faster, right? Often in short cycles, like sprints.
Exactly. And because you have working code, maybe every few weeks, both static testing like reviews and dynamic testing, they can happen and often need to happen within each of those iterations.
Which means you need feedback fast.
Super fast.
Yeah.
And this is critical. It means you need a lot of regression testing. Because every time you add a new feature or fix a bug, you risk breaking something that was already working fine.
Ah, okay. And that explains why Agile, as the source mentions, tends to favor lighter documentation. No point writing huge test plans way in advance and really leans heavily on test automation.
Precisely. That automation is what makes all that frequent regression testing actually possible. You just can't manually retest the whole system every 2 weeks. It wouldn't scale.
Makes sense. But what's interesting is the source also says, look, even though these models are so different, there are some underlying good testing practices that apply pretty much everywhere.
Yeah, definitely. The idea that for every development activity, there really ought to be a corresponding test activity. It's about building quality and, quality control throughout, not just checking at the end.
And ensuring the different levels of testing, which we'll get into later, have distinct goals. So you cover everything without, wasting effort testing the same thing multiple ways.
Good point. And this next one is huge. Test analysis and design. Ideally, that starts during the related development phase. Don't wait until all the coding is done.
That feels like the core of testing early, doesn't it?
It really is. And it connects directly to having testers review things like requirements or design documents as soon as they're available, even in draft form. Finding a mistake in a document costs, minutes to fix.
Compared to finding it after it's coded.
Exactly. Could be days, weeks, huge cost difference. That early engagement, finding defects early, that's fundamental to what people call shift left.
Okay, speaking of shifting left, the source goes even further. It talks about approaches where testing isn't just done earlier. It actually drives the development itself.
Yes, the test-first approaches. This is where TDD, ATDD, and BDD come into play. These aren't just ways to test. They're actually developing practices where you define the tests before you write the functional code. It's a really powerful way to embed that early testing principle, that shift-left idea.
Okay, that sounds backwards almost. Write tests before the code. How does that work? Walk us through TDD, for example.
Okay, TDD, test-driven development. It's a very tight cycle. First, you write a really small, specific test case for a tiny bit of functionality you want. Naturally, that test fails because the code doesn't exist yet.
Right.
Then, you write only enough code to make that specific test pass, nothing more. Once it passes, you refactor, you clean up the code you just wrote, and maybe the test itself to make it cleaner, more maintainable. Then you repeat. Write another failing test, make it pass, refactor.
So the tests are literally guiding the coding step by step.
Exactly. It's like you're writing instructions for yourself before you build the thing.
Interesting. Okay, what about ATDD? Acceptance Test-Driven Development.
So ATDD shifts the focus slightly to acceptance criteria. These are the conditions the software must meet to be acceptable to the user or stakeholder. Often these criteria are defined collaboratively, maybe during design. Then, tests based on these criteria are written before the application code that satisfies them is developed. It's about defining done from a user perspective first.
And BDD, Behavior-Driven Development, that involves non-technical folks more, right?
Yeah, that's a key aspect of BDD. It aims to describe the system's desired behavior using simple, natural language, often in a format like given when then. Given I'm a logged-in user, when I click View Cart, then I should see the items in my cart.
Okay, very clear.
This makes the specifications understandable for everyone, developers, testers, business analysts, product owners. And those natural language descriptions then become the foundation for automated tests, again, ideally written before the code. It really helps bridge the communication gap between the business side and the technical side by focusing on observable behavior.
And the beauty of all these TDD, ATDD, BDD is that those tests you write up front, they don't just disappear, they become part of your automated test suite, used for ongoing quality checks and, crucially, for regression testing later on.
Absolutely. They form a living documentation of how the system is supposed to work, and they're invaluable for ensuring quality over time. And these approaches fit really well with more modern ways of working, particularly DevOps, which the source also covers.
Right, DevOps. The document describes it less as a specific tool or process and more like an organizational culture shift.
Yeah, exactly. It's about breaking down the traditional silos between development, which definitely includes testing and operations teams, getting them to work together synergistically towards common goals, like delivering value faster and more reliably.
And some key aspects mentioned are things like team autonomy, fast feedback loops, integrated tool chains, and a big reliance on CI/CD, continuous integration, and continuous delivery.
Right. That CI/CD pipeline is central. It creates a smooth, automated path for code to travel from a developer's machine, potentially all the way into production.
So for testing, what are the big advantages of working in this kind of DevOps environment, according to the source? Sounds like there are quite a few.
Oh, definitely. The most obvious one is incredibly fast feedback. Because code gets integrated, built, and tested frequently, sometimes multiple times a day with CI, you find out almost immediately if a change broke something or hurt performance, not weeks later during a dedicated test phase.
And CI itself helps with shift left, doesn't it? Encouraging developers to run tests before they even commit their code.
Exactly. Developers are often expected to submit code along with passing component tests and maybe results from static analysis. Quality gets built in earlier. Plus, that whole automated pipeline makes setting up consistent test environments much easier and faster.
What else?
Well, you get better visibility into non-functional aspects like performance or reliability because you can monitor them continuously as code flows through the pipeline. The sheer amount of automation reduces a ton of repetitive manual testing.
And that regression risk we talked about with frequent changes.
DevOps, with its focus on automation, is designed to tackle that head-on. You can build and run comprehensive automated regression suites across the pipeline, significantly reducing the risk of unintended consequences.
But the source is realistic too. It mentions challenges. DevOps isn't just flipping a switch.
No, absolutely not. Setting up that automated delivery pipeline requires significant thought, planning, and effort. choosing, integrating, and maintaining all the necessary tools for CI, CD, testing, monitoring. That's an ongoing investment in both cost and expertise.
And building and maintaining all that test automation.
That's a huge effort in itself. It requires skill, time, and discipline. It's not a one-off task.
And importantly, even with fantastic automation, the source stresses that manual testing still has a crucial role, right?
Definitely. You can't automate everything.
Okay.
Exploratory testing, usability testing, checking things from a genuine user perspective that still requires human insight and creativity. Automation is powerful, but it's not a complete replacement for human testers.
Which brings us back nicely to that principle underlying a lot of this shift left.
Yes, let's really nail this down.
Okay. So the source defines shift left simply as moving testing activities earlier in the life cycle. It's not about eliminating later testing, but deliberately putting more effort into quality up front.
And the why is compellingly simple. Cost and effort. Finding a defect earlier is just vastly cheaper and easier to fix. An error in a requirement stock. Easy fix. That same error found just before release, or worse, in production. That's potentially a massive headache.
The source gives concrete examples of shift-left practices. We've touched on some like testers getting involved early, reviewing specifications to find ambiguities or gaps before coding starts.
Or writing test cases before the code is done. Maybe even using things like test harnesses or unit test frameworks to test code as it's being written, like in TDD.
Using CI/CD for that rapid feedback and running automated component tests whenever code is checked in, that's a prime example too.
Definitely. Also, performing static analysis, automated code checks without actually running it before dynamic testing or building it right into the automated pipeline. Even trying to tackle some non-functional testing, like basic performance or security scans, at the component level, instead of waiting until the entire system is assembled.
So the idea is you might invest more time, effort, maybe even initial cost earlier on, but the payoff comes later.
That's the expectation, yes. Significant savings down the road because you're preventing those expensive late-stage bugs or catching them when they're much cheaper to fix.
But it's not just about techniques, is it? The source mentions needing buy-in.
Absolutely critical. Shift left is often a change in process, sometimes even culture. You need support from management, developers, everyone involved. Without that buy-in, it's really hard to make these practices stick and be effective.
Okay, so we've seen how the process influences testing, how testing can lead development, fit into DevOps, the value of shifting left. How do teams actually get better at doing all this over time? The source talks about retrospectives.
Yeah, retrospectives. Yeah, these are basically structured meetings for the team to reflect on how things are going and identify ways to improve. They can happen at different times, end of an iteration or sprint, after major release, or really any time the team feels it's needed.
And it's not just for testers, right? The whole team participates.
Ideally, yes. Developers, testers, product owners, scrum masters, whoever is involved in delivering the software.
And what do they discuss?
The core questions are usually pretty simple but powerful. What went well? What should we keep doing? What didn't go so well? What should we try to improve? And crucially, how are we going to implement those improvements and make sure we continue the successes?
So you come out with actual action items.
Exactly. And those outcomes and actions should be recorded maybe in a test completion report or team wiki and followed up on. Otherwise, it's just a talking shop.
Makes sense. And for testing specifically, what are the benefits?
Oh, several. Retrospectives can directly lead to more effective testing, maybe finding better ways to identify important bugs, or more efficient testing, finding ways to do it faster or with less effort. They can improve the quality of the test assets themselves, test cases, scripts, data.
And in teamwork.
Big time. It fosters shared learning and strengthens team bonds. Plus, it can indirectly improve the quality of the things you test against, like requirements, because if unclear specs cause testing problems, that's likely to come up and get addressed.
So overall, it's a key way to improve collaboration and just get smarter about how development and testing work together.
Precisely. It's that continuous improvement loop in action.
All right, let's shift focus slightly and look at how testing activities themselves are organized. The source breaks this down into test levels and test types.
Right. Test levels are basically groups of test activities that are managed together and often happen at different stages or scopes within the development process. You can think of it like zooming in or out from testing a tiny piece of code up to testing the entire system interacting with others.
So different levels of granularity.
Exactly. There are different applications of the overall test process, focused on different parts or aspects of the software as it gets built.
And how do these levels relate back to the SDLC models we talked about earlier?
Well, in a strict sequential model, You might have very clear boundaries and formal handoffs between levels, finish component testing before starting integration testing, and so on. In iterative models, there's often more overlap. You might perform activities from several levels within a single iteration as you build out a slice of functionality.
Okay. The source lists 5 main levels. Can you walk us through them, starting with component testing?
Sure. Component testing, often called unit testing, is the most granular level. You're testing the smallest testable pieces of the software in isolation, maybe a single function, a method, a class, or a module. Developers typically do this themselves, and because the component is isolated, you often need supporting code, like test harnesses or frameworks, just to run it and check its outputs.
Makes sense. Next level up, component integration testing.
Right. So once you have individual components that seem to work in isolation, you need to test how they work together. This level focuses on the interfaces and interactions between those components. Does component A pass data correctly to component B? Do they handle errors between them properly? The specific approach here depends on how you choose to integrate, maybe bottom-up, top-down, or integrating larger chunks at once.
Okay, components working together. Then we zoom out further to system testing.
Exactly. Now you're looking at the entire integrated system or product as a whole. The focus shifts from how the pieces interact to the overall behavior and capabilities of the complete system. Does it meet the specified requirements, both functional what it does and non-functional how well it does it? This is often done by an independent test team working from system specifications or user stories. And for some tests, especially non-functional ones like usability, you might need a more realistic environment.
You mentioned non-functional. We'll get more into test types soon, but system testing covers both.
Yes, system testing is where a lot of end-to-end functional validation happens, but it's also a critical place for non-functional testing like performance, security, reliability, etc.
Okay. Then there's system integration testing. That sounds very similar to system testing. What's the difference?
It's a common point of confusion. Component integration is about pieces inside your system talking to each other. System integration is about your whole system talking to other external systems or services.
Ah, okay. Like interacting with a third-party payment system or an external database.
Precisely. Does your application communicate correctly with the external API? Does it handle network issues gracefully when talking to another system? This level often requires test environments that closely mimic the real production environment, including those external connections.
Got it. And the final level is acceptance testing.
Right. This is the highest level, and the focus is squarely on validation. Does the system meet the needs of its users and stakeholders, and is it ready for deployment? It's often about gaining confidence that the system delivers the intended business value. Ideally, the actual end users or stakeholders perform this testing.
And the source mentions different kinds of acceptance testing.
Yes, things like user acceptance testing, UAT, is common, where users perform tasks in a realistic scenario. Operational acceptance testing checks readiness for operation and maintenance. There might be contractual or regulatory acceptance testing based on specific requirements. And you also have things like alpha testing, internal and beta testing, external users, before a full release.
So these levels are distinguished by, let's see, what you're testing, the goals, the basis for testing, like specs versus code, the kinds of bugs you expect to find, and who typically does it.
That's a good summary. Now, distinct from levels are test types. If levels are about scope or where you test, types are about what's quality characteristic you're focused on. And a given test type can usually be applied at multiple test levels.
Okay. The document calls out 4 main types. Let's start with functional testing.
Functional testing is all about evaluating what the software does. Does it perform the functions it's supposed to, according to the requirements or specifications? We're checking for correctness, completeness, appropriateness of the functions. Does clicking the Save button actually save the data? Does the calculation produce the right result?
Straightforward enough. Then, non-functional testing.
This evaluates how well the system performs or behaves, looking at characteristics other than its core functions. The source uses the ISO 25010 standard for examples things like performance efficiency, how fast is it, how much load can it handle, compatibility, does it work across different browsers, operating systems, devices, usability, is it easy to learn and use, reliability, how often does it crash or fail, security, is it protected against threats, maintainability, how easy is it to modify or fix, portability, can it be easily moved to another environment, and safety, does it avoid causing harm?
So functional is what it does, non-functional is how well it does it across various quality dimensions.
Exactly. And while we often think of non-functional testing happening later, like in system testing, it's really important to consider it early too. You can review architecture for performance implications, or even test the performance of individual components. Finding a major performance bottleneck or a critical security flaw just before release is, well, it's bad news. Very risky, very costly.
Yeah, definitely want to avoid that.
hmm
Okay, the other two types relate more to how you design the tests.
Yes, black box testing. This is also called specification-based testing. You derive your test based purely on the external specifications requirements, user stories, use cases, without looking at the internal code or structure. You treat the software like an opaque box. Put inputs in, check if the outputs match what the spec says.
So you don't need to know how it works inside.
Correct. You're focused entirely on the external behavior against the documented requirements.
And the opposite is white box testing.
Right, also called structure-based testing. Here, you do use your knowledge of the internal structure, the source code, the architecture control flow, data flow, to design your tests. The goal is often to achieve a certain level of coverage of that internal structure, like making sure every line of code is executed, or every decision point in the code is tested both ways.
Okay, so black box looks from the outside, white box looks from the inside.
That's a good way to put it. And again, the source makes the point that these types aren't restricted to one level. You can do black box testing of a single component against its spec, or white box testing at the system level by looking at architectural pathways, functional testing at the integration level, non-functional testing at the component level. They mix and match.
Got it. Now, software is rarely static. Changes happen, new features, bug fixes. The source talks about specific testing needed for that, confirmation and regression testing.
Yes, these are absolutely critical whenever changes are made. Confirmation testing is the simpler one. It's purely about verifying that a specific defect that was previously found and reported has actually been fixed successfully.
So you run the test that failed before and check if it passes now.
Pretty much. You rerun the steps that expose the bug to confirm the fix worked, and the bug is gone.
Okay. And regression testing, that's the bigger one.
It usually is, yeah. Regression testing is about making sure that the change you made, whether it was that bug fix or adding a new feature or even updating the environment, didn't have any unintended negative consequences on other parts of the software.
Did fixing bug A accidentally break feature B? Did adding feature C slow down the whole application?
So it's checking for side effects.
Exactly. Unwanted side effects in the same area, in different components, maybe even in connected systems. It's about ensuring the change didn't break anything that used to work.
And before just randomly retesting everything, the source recommends doing an impact analysis. Highly recommended. Impact analysis is the process of figuring out which parts of the system could potentially be affected by the change that was made. This helps you intelligently scope your regression testing. Instead of wastefully retesting everything, you can focus your efforts on the areas most at risk. Makes regression testing much more efficient and effective.
And because these regression tests need to be run over and over again, especially in iterative or DevOps environments where change is constant.
They are prime candidates for automation. Building and maintaining an automated regression suite is probably one of the most valuable uses of test automation. Running these tests automatically, frequently, maybe as part of your CI pipeline, gives you a huge safety net against introducing regressions.
And confirmation and regression aren't just end-of-project things, right? They apply at all levels.
Absolutely.
Yeah.
If you fix a bug in a single component during component testing, you do confirmation testing for that fix, and probably some regression testing within that component or related components at that level. Same goes for integration, system level. Whenever a change is made at a certain level, confirmation and regression testing relevant to that level are needed.
Okay, that covers changes during development, but what about after the software is released? Testing doesn't just stop then, does it?
Not at all. That's where maintenance testing comes in. This covers testing related to changes made to a system that's already operational out in the wild.
And maintenance isn't just bug fixes found by users.
No, the source mentions several types. Corrective maintenance is fixing those production bugs. Adaptive maintenance is changing the software because the environment changed, like needing to support a new operating system version or browser. And preventative maintenance is making improvements, maybe enhancing performance, usability, or adding small features. These changes can happen in planned releases or as urgent hot fixes.
Impact analysis sounds even more critical here if you're changing a live system.
Definitely. You need to understand the potential risks and consequences of making a change to a system that people are actively using. That analysis helps decide if the change should be made and how extensively it needs to be tested.
And the testing itself. What does maintenance testing focus on?
It generally has two main goals. First, verify that the specific modification, whether it's a fix or an enhancement, actually works as intended. Second, and often more significantly, perform regression testing to ensure the change hasn't negatively impacted the rest of the system, the parts that weren't supposed to change, which is usually most of it.
And how much testing do you do?
The scope depends, according to the source, on things like the perceived risk of the change. Is it touching a critical area? How complex was the change? Also, the size of the existing system and the size of the change itself. A tiny configuration tweak needs less testing than replacing a core module.
Okay, and the triggers for maintenance testing aren't just code changes.
Right. Besides modifications like planned releases or hot fixes, triggers include things like migrations or upgrades of the operational environment. If you move to a new server platform or upgrade the database, you need to test the software in that new context. This might involve testing the environment itself, the software's interaction with it, and any data conversion processes.
And interestingly, the source even mentions retirement, testing when a system is being shut down.
Yeah, it might sound odd, but if a system holds important historical data, you might need to test the procedures for archiving that data. Can it be successfully archived? And crucially, can it be retrieved correctly later if needed for legal or auditing purposes? So, testing ensures the data preservation process works.
Wow. Okay, that really covers the whole life cycle, doesn't it? From the initial SDLC choice shaping everything, through test-first approaches actually guiding development, how testing integrates into fast cycles like DevOps, the huge value of shifting left, using retrospectives to get better, breaking down testing into logical levels and types, and then those critical confirmation and regression checks, right through to keeping things stable during maintenance and even handling retirement.
It really paints a picture of testing not as an afterthought or just a quality gate, but as this continuous thread, this active participant woven throughout the entire process of creating and maintaining software. Sometimes it follows development, sometimes it leads it.
It definitely shifts the perspective away from testing just being that final check. So thinking about testing in this way as integrated, sometimes driving, always present, how does that maybe change the way you, our listener, think about software quality, whether you're involved in building it or just using applications every day, something to perhaps mull over?
Yeah, definitely food for thought.